Good morning, good afternoon, good evening, wherever you are in the world. Thank you so much for joining us today. My name is Sarah Alspaugh, and I will be your webinar host coming to you from Cincinnati, Ohio, here in the U.S. I'd like to welcome you to today's webinar, our topic, Space CAE and Hardware Qualification. And I would like to welcome and introduce our speakers today, and then I will turn things over to them. With us, we have Mr. Chokri as well as Mr. Podar. Again, I'll just tell you a little bit about them briefly and turn things over. Mr. Chokri has a Master in Mechatronic Engineering at the KU Leuven, Belgium. For more than 20 years, he's been experienced at Siemens. He started in product development with a focus on NVH testing solutions. Later, he moved to providing professional services for the automotive and aerospace industries. Today, Mustafa is a senior business development manager for the aerospace and defense industry with a focus on introducing new testing technologies to the market. And with us, we also have Mr. Podar. Mr. Podar has been ADS EVT since March 2017, and previously he was a vibration test engineer at AS System. His main skills include mechanical test and mechanical engineering, management of test team, and follow-up test faculty and sensors. We're very excited to have both of you here today. I'm going to go ahead and turn things over to you first, Mustafa.
Welcome to this live webinar where we will look into technologies for safe and efficient spacecraft integration and qualification testing. Let me start with an exciting date, May 30 this year. Probably many of you will remember this date and recognize on the picture the Falcon 9 launcher of SpaceX. It was a special day in the sense that it was the first time in history that astronauts were launched towards the International Space Station on a commercial spaceship. The first 12 minutes of the launch and the final safe release of the Crew Dragon capsule in orbit were probably the most exciting and at the same time stressful moments because a lot could have gone wrong during that short period of time. In fact, this concern applies in fact to any space mission, and that is what we will talk about in this presentation. During the takeoff and the first couple of minutes, the spacecraft is exposed to an extremely harsh environment, causing extreme levels of vibrations and shocks that can lead to damage of the payload or even the entire spacecraft. So therefore, ensuring launch survivability through qualification testing is really crucial and mandatory to ensure. Before we continue, I want to highlight some trends we see in the space industry. The number of space missions will only increase in the future. Today, we already see a space race between the traditional space agencies and many newcomers. This creates a new momentum, let's say, in the space industry, which drives manned explorations to the moon or Mars. Also, let's say, investigations to make launching of satellites much cheaper. Also, space tourism is getting more and more attention. And of course, terrestrial applications where systems need to be put in orbit in order to support, for example, autonomous driving and so on. Here we see the flight profile of a launch vehicle with the various phases during the launch. In each phase, the passenger satellite is exposed to a very specific, extremely harsh environment, leading to extreme levels of vibrations. Throughout the launch, the vibrations are structure-borne and airborne in nature. After liftoff and before deployment in orbit, there are also a series of violent shocks, like, for example, the stage separations, pyro balls, and ultimately also the release to orbit. And all these shocks, in fact, they put the satellite under a lot of structural stress. Once in orbit, then life is a lot quieter, of course. Therefore, launch vehicle authorities impose strict mechanical qualification testing that represent real launch conditions for each component as well as for the assembled satellite before it can take a flight on their launcher. All the requirements are described in a launcher's user manual. Here you see the specs of the Soyuz launch vehicle. They impose sign, random, acoustic, and shock tests and ask for proof of those tests. They are often also present during the testing. Challenges are that those tests happen on the actual spacecraft, so there is a significant risk of damaging the hardware. And that is one of the, let's say, key messages in qualification testing, is namely how to perform a successful qualification testing without damaging the spacecraft. Because if you damage the spacecraft, it will introduce delays, costs, and so on and so on. So let's say testing application, testing software and hardware needs really to be, let's say, designed in such a way that it can perform qualification testing with full confidence. So in this presentation, I will focus on the following topics. So I will first talk about qualification, let's say the different type of qualification testing. Then I will introduce some smart innovations, and then later on I will also talk about some engineering tools that can bring insights. And at the end, we will have Mr. Podar from Airbus, who will present some of SimCenter applications in their qualification testing. So, space hardware mechanical testing covers, in fact, a wide frequency range involving many different test types and different test infrastructures. Shakers, slip tables, reverberant rooms, speaker setups, drop tables, pyro shock test bench, and so on. So the nature of those tests is quite different. This presents some challenges. First of all, it's a challenge for the test team, as they have typically to master as much as possible of all the tasks at hand. But also challenges, another challenge is to keep the hard and the software investments under control for all those test setups. Each test setup, namely, has a specific set of requirements when it comes to data acquisition and analysis. So we will see in the upcoming slides how SimCenter solutions cover all these requirements in a uniform platform. A satellite vibration test consists of reproducing the vibration levels described in the launch vehicle manual on a shaker. The control system drives this installation, taking the levels at the interface points into account, closing the loop in real time. At the same time, response levels are being monitored and checked against auxiliary not to exceed levels or maximum levels. If those responses, let's say, are exceeding the prescribed level, the control system will reduce the drive level to protect the instruments. This process we call notching for sine sweep testing, for example, and response limiting for random excitation testing. At the left side here, you see a picture of a BP Colombo satellite at the ESA ESTEC facility. It is a special satellite because, well, it exists in fact of several modules. The module below is a satellite that has been built by ESA. It's a satellite for monitoring Mercury. The next one is a satellite which has been built by JAXA, so the Japanese Aerospace Agency. This is also for investigating the magnetic field of Mercury. And then on top you have another module which is a propulsion module which will in fact drive the two satellites to Mercury. So you see, satellite can, as I say, can be quite complex. So you can, like here, you have a satellite stack, and you have to ensure that when you test the satellite, that you also do not damage any sensitive instrument or file or damage the integrity of the whole equipment. As I said, spacecrafts are getting larger and more complex. This triggers the need for higher channel count systems for extra protection and better understanding of the spacecraft dynamics. To allow large configurations without overloading the control system, we designed reduction systems. Those are extensions to the control system, fully synchronized to the control system. They acquire and store the raw time data, but in parallel, also process the data in real time to spectra or FRF and so on. This processing is controlled by the synchronization channels generated by the control system. This setup allows the control system to focus on safety critical control and notching tasks, while the reduction system can acquire all the remaining channels. The setup that you see here in the middle is in fact the setup at ESA Aztec, where they have been using 60 control channels and more than, I think, 500 or 600 channels or more for reduction. Good. In order for the vibration test team to define the qualification test with maximum confidence and ensure the space hardware will not be damaged during the test, a notching and limiting prediction application has been developed. This tool predicts what the spacecraft will endure during the test. This prediction uses data from the control and one or more reduction system channels. The prediction can be done using data from a low level run or from a self-check run, and is then extrapolated to higher excitation levels. So it enables a full simulation of a test run, providing maximum protection. It allows, in fact, offline limiting, embedding the linearly extrapolated levels in the reference spectrum, while still keeping the limiting profiles active for additional protection, especially when you have non-linearities, which of course are not taken into account in this offline limiting estimation. These channels then can still protect then the spacecraft. For lateral tests on spacecraft, sleep tables are commonly used. Those tables are designed to be uniform, having the same acceleration level regardless of the position on the table. This only holds up to a certain maximum frequency, above which the table acts as a dynamic system. Labs are often forced to use the table above this frequency because there is simply, let's say, no alternative. It is thus important to properly understand the table dynamics when designing the test setup. Tables have resonances and anti-resonances, so knowing those and the associated mode shapes is important when selecting the location of the control accelerometers and defining frequency-dependent contribution profiles for the control sensors. In this example here, in this picture, it was a setup where they have used 13 accelerometers and performed a operational deflection shape analysis and also an operational model analysis to investigate, let's say, the dynamics of this shaker table. So I have put here two mode shapes of this table. So the first flexible mode was around 570 hertz. So that means that we have to be careful if our frequency range of interest is above this frequency. And also here in this first flexible mode, you see that one point here is really acting as a nodal point. So it is dangerous if, let's say, if you put a control channel there, because that will then not really give the right information to the control algorithm. To mitigate risk of failure during deployment and conduct successful qualification tests, simulations are used to study the dynamic behavior of satellites. NX Nastran and SimCenter Structural Dynamics, for example, have traditionally a wide customer base in aerospace and defense. Here I'm showing you an example of Lockheed Martin Space System, where they using this simulation for coupled load analysis and the study of the dynamic behavior of a satellite and its solar panels upon launch and deployment. Interesting here is that a unique feature to SimCenter Nastran is namely the ability to create external super elements with mode acceleration, output transformation matrices, which are required for coupled loads analysis. The system that I just described for vibration testing can in fact also be used for acoustic qualification testing. The same, let's say, hardware, and in fact, a similar on the same platform, a similar application for acoustic control. A satellite acoustic test consists of reproducing acoustical levels as defined in the launch vehicle manual in a reverberant room. The control system drives the installation, taking levels measured on an array of microphones into account, closing the loop in real time. At the same time, response levels are being monitored. Those responses are typically accelerations or strain levels. Typically, up to 60 microphones are used for control, and on a large and complex spacecraft, 500 to 700 channels are measured on a reduction system. If those and some of them and some channels, of course, also are used for, let's say, protection of sensitive hardware, and if those responses are exceeding the prescribed level, the reduction system can be set up to abort the test, for example. So SimCenter testing solutions allow to perform such acoustic qualification testing in a reverberant room with full confidence. So it offers safe, traceable, efficient, and smart control capabilities to ensure protection of the hardware and reaching the desired third octave acoustic profile. And what is also very important in or crucial in all these different qualification testing is the self-check test. Self-check test is in fact a low-level test that is conducted prior to the full-level test in order to verify the closed-loop condition, to predict some full-level, let's say, responses, and also to see where limiting is required and so on. So that is really one of the let's say really crucial steps in a qualification test. But we will talk about that later on in the presentation. The SimCenter, let's say, sorry, excuse me, the SimCenter SCADAs, lab hardware and test lab software can also be used to acquire and analyze shocks. It allows a safe reproduction of a wide range of shocks on shakers and provides all necessary processing capabilities, such as online calculation of shock response spectra and SRS limiting for specimen protection. Okay, so shocks are also often reproduced using pyrotechnic devices instead of shakers. Spacecraft separation mechanisms use pyro devices, causing a high-level shock. This shock propagates through the entire spacecraft. Primary purpose of the test is, of course, validating that the separation mechanism works as designed. It is, however, also important to study the impact of this shock on the instruments on board the spacecraft. For that purpose, acceleration levels throughout the spacecraft are measured during the test. Typical analysis results are shock response spectra for each of the measurement locations. Sorry. So this brings me to the next chapter, where I will introduce some smart innovations. Spacecraft acoustic testing is typically performed in a reverberant room, using high-power acoustic modulators to reach the extreme large acoustic levels. But in fact, it can also be done in a non-reverberant room, using conventional loudspeakers. And that is, of course, very interesting because that could be a very, let's say, a cheaper alternative, because there is no need for building a reverberant room. So that means lower construction costs, lower operating costs. And also, it offers the, let's say, the advantage that you don't have to transport your test specimen to a dedicated laboratory to perform the acoustic test. So it reduces the risk of damaging the structure during transportation. The technique that is used is called direct field acoustic noise. testing and requires a multiple input, multiple output, narrow band control technique to ensure the acoustic field is uniform. So here in this example, you see a setup of a satellite component, and instrumentation that is used is during such a test are microphones for control and a set of additional microphones for acoustic field uniformity check. So direct field excitation with SimCenter testing solution is a very efficient way, I said, of validating newly designed hardware. So it allows to explore more variants with the possibility to perform immediate validations in your lab. In preparation of the actual direct field acoustic noise test, virtual direct field acoustic test can be executed to design and optimize the test setup and perform the acoustic test virtually. In this example, the target setup is the DFAN test on a reflector of an antenna. In preparation of this test, the setup was designed in SimCenter 3D, including the arrangement of the speakers and the position of the microphone and the test specimen. Then the performance has been predicted, including the uniformity of the acoustic field. Finally, also calculations on the test specimen itself have been done, so to calculate the acoustical induced loads on the test item. So as I said, SimCenter SCADAs is used as hardware to generate the controls signal to the shakers and for the acquisition of the data from all the sensors and spacecraft. So we continuously, let's say, innovate also our hardware. And what you see here is the SCADA's TCF4 module. It's a very flexible module in the sense that it allows you easily to, let's say, to switch between ICP and charge sensors. And it has also, for the charge input, a very large range, allowing you to use that for force limiting. It is also robust against ground loops because it has a floating input mode. Additionally, the module also has an output connection, allowing you to record the input channels on a recorder or on a reduction system. Again, adding redundancy for the confidence of the test. A very nice and powerful module, which in fact combines robustness, redundancy, and flexibility. I will talk about virtual shaker testing now. So virtual shaker tests can help to predict major issues that might occur during the physical test, such as unacceptable high vibration accelerations that may occur and damage the satellite or expensive and sensitive instruments on that satellite. Also, when, for example, the satellite that is being tested is very heavy, large, and has a weight which is comparable to the shaker, it can form a new product shaker coupled system with unknown dynamic properties. So in fact, its behavior is unpredictable in the physical test, and there virtual shaker testing can help you, let's say, to mitigate the risk and to investigate how this coupled system will react, let's say, on the qualification test. There are different ways to perform a virtual shaker testing. So you can have an approach where everything is done with FE models. So you have a detailed FE model of the shaker and the satellite and an implementation of the control algorithm. You can have a hybrid approach. But an interesting approach is the experimental driven approach. This is a relatively fast and reliable methodology. It doesn't require any assumptions on modeling, coupling, and interfaces. So the models that are used here are in fact experimentally derived from FRF measurement or from the self-check data. Good. Let's now move to the next topic, so engineering insights. To really understand the structural dynamics of a spacecraft, the program sometimes requires a dedicated test like a model survey test. This test aims at test validating the spacecraft FE structural dynamic model. This model is necessary for the launcher coupled loads an analysis process which assesses the risk of launch load damage. The same model can also be used to de-risk qualification testing, predicting spacecraft response to the loads injected during the test, which in fact corresponds with the virtual shaker testing I just talked about in the previous slide. Such model survey test consists in fact of exciting the structure with electrodynamic shakers and measuring the responses with accelerometers and then applying model parameter estimation algorithms to derive the model parameters. It also allows you to, for example, to perform nonlinear analysis, for example, by applying a sine or sine type of excitations. So SimCenter fully supports this process and provides all necessary capabilities for performing virtually or physical model analysis of space structures. Let's illustrate this with an example of a program where such model survey test was recommended. So it was for the RadarSat, a Canadian Space Agency project. The coupled loads analysis that has been conducted on this list, on this satellite, has revealed that damage during launch could occur on the radar panels. So this satellite has 4 radar panels, which have almost identical geometry, and they are stacked closely together in launch configuration. So an in-depth and accurate identification of the resonance frequency was required to calibrate the FE models. As a result of the high model density, the test that has been conducted here required 5 simultaneous shakers and a total of 240 responses to isolate all the modes. Good. As we have seen before, an acoustic test can also be done using conventional speakers. So we call this the DFAN method. Here you see a setup on a satellite component, the reflector of a downlink antenna. Instrumentation that is used here, so that is used during such a test, are microphones, as I said, for the control, and a set of additional microphones for acoustic field uniformity check. But of course, we also measure additional responses like accelerometers and sometimes also strain gauges. Traditionally, those accelerometers and stray signals are processed towards PSDs to get an idea about the acoustical load-induced loads. But you can in fact also use them to gain more engineering insight. And for example, if you can use the operational model analysis to extract from the accelerometer data the model parameters, you can have an idea of what are the resonances, what are the mode shapes, and also the damping, which is interesting information. Another interesting application is satellite micro vibrations. High-end optical imaging sensors and lasers are used more and more in satellites. These sensors have high requirements in terms of stability to provide high-quality images. If you look here on the slide, you see at the left side 2 pictures of an image taking on Earth, and you see that the right image is really blurred, shows distortion, in fact, which were caused by reaction wheels vibrations, these micro vibrations. So as I said, mechanical devices on the spacecraft, such as reaction wheels for attitude control, can cause vibrations leading to blurring of images. These issues need to be solved by understanding the vibration energy generated by these devices, and also by looking at possibilities to reduce the energy transfer to the sensitive equipment. So we see today that many testing agencies are having this type of test rigs. So here you see a test rig for to characterize microvibrations at ESA ESTEC. So they have here a dedicated test where they measure the vibration and loads generated by the flywheel, by this flywheel here on this setup. You see that the setup has been mounted or placed on a granite table, and this is done because the level that are measured are so low that there is a need to isolate the test rig from ambient noise and vibrations. The SimCenter SCADA's hardware is ideally suited for this kind of measurement because it has an ultra-low noise floor, allowing accurately measurement of low-level vibrations. On the lower right picture, you see also a small shaker. This is the Q source. It's a mini shaker that we also develop and which allows, in fact, to measure transfer function. The nice feature of this type of shakers is that they have a force sensor built in, and they also allow to align themselves automatically, so there is no need of alignment of stingers and so on. So it's easy to set up and to start with measuring transfer functions. Okay, so this brings me to the first part of this presentation. Sarah, I will now pass the word to Mr. Podar for his part, where he will talk about the application of SimCenter in his facility.
So hello to everyone. I'm Mr. Podar. I'm leading mechanical test and vibration test, acoustic test, and also physical measurement in Airbus Defence in Space Toulouse. So I will make a short presentation of the applications that we have in Airbus Defence and Space for using the software of SimCenter and also the hardware and all the applications that we have. So shortly, I will present the Airbus Defence and Space business. So some people know that we have the first company in Europe for satellite covering. We provide telecommunications spacecraft for other country and the Earth observation spacecraft for the pictures and so on. We provide also navigation spacecraft, orbital space exploration for science mission for like dark matter with Euclid. We have also the rover ExoMars, but we have some delay with the COVID, but it will be launched in 2022, I think. And we also provide a full solution for satellite testing. So here I'm in Airbus Defence and Space environmental testing in the Toulouse premises. HDSCVT Toulouse is the urban leading test space center. It was formerly in test space for all people who know it in test space at before, but now we are Airbus Defence and Space. It is one of the 4 European test centers coordinated and approved by ESA to carry out test service to the benefit of large international industries on the space domain. So if you give us a spacecraft, we can arrange to do the full test campaign, the mechanical test with shaker, acoustic, shock test facility, drop test, the physical measurement, and we can also carry the thermal test and the EMC with anechoic chamber, magnetic chamber, and so on. So in this slide, I will show you that all the applications that we have with the hardware of SimCenter and how it helps us to carry out all the tests. So you can see the tests that we can carry with SimCenter. So vibration test, acoustic test, acquisition test, microvibration, and FMD. I will explain it later. We use this module to carry out the test. So sign control, random control, shock control. We have 4 shakers in the test facility. Each test facility uses the software of SimCenter and the hardware also. So we can carry for small subsystem to huge spacecraft, because with this shaker we can put a spacecraft to 7 or 8 ton maximum on the shaker. So it's a huge spacecraft with a high massive effective mass on the first mode. So we can carry all the tests for all the solar array, everything, reaction wheel, so subsystem for space agency, and so on. After the vibration test, we can carry the acoustic test. So we measure the microphone with microphone and all the accelerometer on the spacecraft. We can also make the acquisition test with the transient capture mode from the SimCenter software. We can carry the clamp band release. The clamp band release is we need to check with the launcher that the clamp will between the adapter of the launcher and the spacecraft will be released correctly, and we measure the pyrotechnic choke with LMS software, the SimCenter software. We also carry the solar array deployment in order to check that the solar array will deploy correctly in the space. It's better. We also, like Mustafa present us, we have a test bench for the micro vibration also, and we monitor it with the sign control. And this is the last test bench that we have investigated last year. It is the FMD. The FMD is the first force measurement device, and we use the sign control with direct channel, but I will explain it later. In our parameters, we have an park homogeneity. We have made the choice of homogeneity of the AVT park. We use a SCADA slab on each test facility for high flexibility of our customer. We choose the configuration with customer requirement. Does it need to notch on strain gauges? How many channels is requested? How many load cells needed? SimCenter has developed VCF card for us, and it's very robust and it's also high flexibility because you don't need to make the difference between charge or ECP channel. You can easily channel separately if you have one loop on one channel. You can see in this example that you can have high flexibility because you can make just one test with just a piloting system and you have few channels, but you can add the strain gauges acquisition, and you can notch on this strain gauges, but you can want another system with a high number of channels. So the maximum that we can carry on those furnaces is 500 channels on the acquisition system and 100 channels on the piloting. So we have two systems. I don't know if you know well this kind of system. There are one for the piloting system. We put the pilots and the control pilots on this system, and also the notch channels. On the acquisition system, they will have all the channel of the spacecraft. All the channel of the spacecraft is taken with the acquisition system with the VCF card, and we have recopy on this channel, and we choose some critical channel we put on the piloting system, and that's the thing that we carry all the tests in our premises. So this is the modular capacity example. It takes just 1 hour, maybe less, to pass to one configuration. That it is a standard configuration for a spacecraft with this number of channels, and you just need to put a mobile acquisition system that we have on, because we have all the same SCADA slab, and if we want to add some SCADA slab, we just need to connect it with optical fiber, and in half an hour you can add a lot of channel of your acquisition system. So this is the thing that we need. I will explain now an utilization of the sign control. I will explain the safe check, because for us it is the half part of the test, because we need to guarantee before the test that all the security will be okay and all the channel will be okay. So with the safe check, you can check that correct axis on the pilot accelerometer, the predicted response on critical accelerometer. You have the estimation of the system transfer function, and you can check with high precision that the main mode of the spacecraft will be okay. and you can have also the prediction of notch driver. On this example, I have superpose with a pink curve and the blue curve. The blue curve is the test run that we have passed, and the pink curve is the self-check we have performed before the test. So you can see here that they are very near, and for us, we have a lot of information just with the self-check. We can check that the main one is where we have predicted, so it's the first information. You can check that you have the correct level at low frequency, so you don't put a channel in the wrong side, so you can check it, and you can check that the notch channel is a correct one, and you can check if this channel will take the end during the test. You can check that for this one, this is the main mode, so this will be take the end here, but you can see that there will be another notch will take the end for at other frequency. So self-check result is a part of our process. We check the self-check during like 20 minutes before each test. So it's very, very important, and the sim center allow us to verify that it is very, very, very effective. I will explain another thing. The control spectrum main mode with automatic notching, because this is always a discussion between the customer, the launcher, and also the mechanical architect. The discussion is about to qualify in terms of effort and moment, and to see if the spacecraft will handle the launch. But the architect wants to protect the structure and also the sub-equipment, but the launcher wants to pass a lot of moments. But we need to have a long discussion. So you have two ways to do this. You can manually decrease the input, but you need to do the calculation, and if there is some mistake, you don't have protection. The second way is to use the automatic notching. So you can see that we can perfectly control the input of the mode. If you want to understand the compression factor in the software and the number of period, you can control the overshoot. You have in green the reference and in red the abort. You can, if you want to understand, you can control the overshoot, and you can also control the instability after the main mode. You need to know that for a main mode of spacecraft, it's like 4 or 3 tones on the effective mass, with a Q factor of 30. So it's better to control it with a lot of safety, and the automatic notching is working very well if you understand how the compression factor is working and the number of periods. But you need to understand how your shaker is working, and you need to know also the finite element. You need to know well the finite element of your spacecraft. But if you know everything, you can pass a test in 1 day maximum by axis between the low level, the extrapolation of the low level, after the acceptance and the qualification, and after the low level. So you can carry in 1 day. If you check the self-check, and if you check correctly your automatic notching, you can pass an axis of the spacecraft with 400 channels in 1 day. So, so now this is the last application that we have in our premises, is to use a derivative channel for FMD application. The FMD is a force measurement device. Using real-time process derivative channel in the Sim Center Test Lab, the last version, the recovering interface force and moment can be used as notch to control the input. So this is derivative channel. It is not a physical channel. You use physical channel to compute the effort of the moment with this formula. And this is the channel parameters of Sim Center. You can see here that we have taken the notch on the moment on MY at 11.8. You can see that we have taken the notch here, and you can see that the force, the sum of the force, has decreased perfectly after that we have taken the hand. And you see here the accelerometer will not take the end because we have choose on this solution to notch on the moment. Some of customer wants to notch on the moment because they are in real time the moment and they don't need to wait all the run and to process the data because they have directly behind their eyes the moment and they can notch on the moment or the effort. So it's very, very effective and we use it a lot of now. Okay. And the last slide for our application is the micro-vibration test facility. The purpose of the micro-vibration, as Mostafa said before, is to measure the interface force and moment in 6 degrees of freedom, which are generated by a specimen. There are two types of tests. There are emissivity test and also susceptibility testing, because we need to know if the reaction wheel will be input some force on other equipment. Like I will take an example, but in the meetup spacecraft will be the next spacecraft for weather forecast prediction. We have two equipment with a rotation wheel, and we need to know if one wheel will have an effort on the same wheel on the spacecraft. So we need to know if we need to check it with the emissivity testing, and we use this application of the sign control on the range of 0.1 Hertz, and you see that the effort and the moment is very, very, very low. So we use a sim center to carry out this test. So voilà. This is all the applications that we use in our premises with a sim center software and the hardware. So thank you, and if you have a question, I will pass the end to Mostafa.
Okay, thank you, Mr. Kovdar, for the nice presentation on some functionalities in SimCenter. So I want to end, oh, sorry, because I had incorporated your presentation in mine, but this is the final slide I want to end with. So to summarize, the SimCenter Test Lab and SCADA solutions consist of a complete solution for mechanical qualification testing with vibration, acoustic, and shock excitation, as well as model survey and microvibration testing for the space industry. The platform is designed to cover all applications in a uniform implementation, covering control, acquisition, and real-time processing. It also supports data and configuration management and easily connects to simulation models. And as I said, we use a common hardware platform for all the different type of application testing. It also combines, as I said, with the SimCenter 3D capabilities for simulation of the spacecraft dynamic performance and for validation of the spacecraft digital twin or FE model. Okay, Sarah, this ends the presentation, so we can go to the Q&A part.
This concludes today's webinar. Thank you so much for being here, everyone, and have a great day.